We've now spent a few videos talking about the different control operations that we have in classical thermodynamics, but we still have more to do. I want to end this lecture by talking about the first and second laws of thermodynamics, which you've probably heard about before. But I'm going to start this with a big disclaimer. Let's use the analogy of classical physics, where we have Newton's three laws. Newton's first law, second law, and third law should allow you, with a couple of other assumptions about kinematics, to tell, or I should say maybe to solve problems in classical mechanics. So for instance, you can apply Newton's second law, F equals ma, in an inertial reference frame that you know about from the first law, and then solve for the motion of a particle over time. You could use Newton's third law to tell someone what the result of a collision between particles would be. All of these kinds of things suggest that the laws should be fundamental. They should explain how the theory works. You should be able to use them as the building blocks for explanations about dynamics. Again, thermodynamics is a control theory, not a dynamical theory, but we might hope that the three laws of thermodynamics work in the same way, that we start with the three laws and then we can derive everything else about the theory from them. But that is emphatically not the case. In fact, there's a bunch more stuff, which we've spent a lot of time now covering, that we need in order to derive what's going to happen when we put thermodynamic systems together or when we do adiabatic work on them. So that disclaimer aside, let's introduce these laws knowing that in fact they are results. They're theorems that we can prove. All right, so the first law says that energy should never be created or destroyed by thermodynamic processes. Okay, so that's fine. The only thermodynamic processes that there are adiabatic work operations and joins. It turns out that this first law, in fact, does give us some information about how to connect the mathematics that we've used to the real world. So let's discuss this first law in the context of both of these operations. So for adiabatic work, we saw that what's going on is the user is going to do something to a simple system. That thing can't change the entropy of the simple system, but it can change the energy of the simple system. So how can the first law be true if adiabatic work can change the energy of a simple system? And the answer is actually not too complicated. It's just that the user either does work on the system or has work done by the system on the user. So the user contributes or gains energy. And this is very familiar. In order to compress a box of gas, you need to push on it, and that will end up doing some work. Good. For joins, this instead functions as a restriction on the subsets kappa on which we can take joins. So only kappas are allowed if they have a fixed total energy. As we saw with the thermal join, the energy of system 1 and system 2 were not independently conserved, but the energy of system 1 plus the energy of system 2 was conserved. And the same thing was true in a mechanical join. We'll see that this is broadly going to be pretty straightforward in most of the sorts of joins that we'll do in this course. But in fact, the first law says that it should be true always of all physical systems. All right, Next, the second law. Wonderful. The second law of thermodynamics says that all thermodynamic processes increase or do not affect total entropy. Now we can offer a very short proof of why this is true. Adiabatic work operations always leave the entropy fixed. For a join, we know that our subset kappa should include our initial point. Because it includes our initial point, we know that we, at the very least, will end up at that point. Since we're going to the, let me say it like this. We end up at the point on kappa with maximum entropy. So either there exists another point on kappa with greater entropy than our starting point, or our starting point has the greatest entropy on kappa. In the former case, we increase the entropy by moving to that other point. In the latter case, because our initial point has the highest entropy on kappa, we simply stay at the initial point, and the entropy doesn't change. So both of these operations turn out to increase or at least leave unaffected the total entropy of the system. That means that both the first and second laws are true based on our former description of the system. Again, just to reiterate, these are things that we can show that our theory leads to consequences of our theory. They are not the same kind of laws that you would see in, for instance, classical mechanics. And with that, I'm finished discussing the basics of control operations. In the next lecture, we're going to start talking about some intensive quantities that will help us to do problems maybe more quickly and with less effort than what we've done here. Until then, I'll say thank you so much for watching, and I'll see you in the next episode.